We now go back to our code to see how to validate the assumptions using Python for our simple linear regression model. We're going to start off by validating linearity. If you remember, linearity states that we expect the relationship between the independent and dependent variable to be linear. And in a way, we've already verified this assumption when we first chose which variable to use as our independent variable. So I'm going to bring back the pair plot from above. This is exactly the same line that we had above to create the pair plot. When we were examining the output to choose which variable of these four candidates we were going to use as the independent variable, we were in a way implicitly choosing the one that best verifies this assumption, because we chose length of membership, the one that exhibits the most clear linear relationship with our dependent variable. So we can happily say that this assumption is verified. Moving on to normally distributed residuals, this assumption states that we believe the residuals to be normally distributed. This is going to be very important in the online practice when we cover inference, because the normally distributed residuals assumptions affects how confident we can be in the p-values associated with each coefficient, and the p-values tells us how statistically significant those coefficients are. So this is very important when we get to inference. First thing we need to note is that for validating these assumptions, it's okay to break away from sort of the clear train test split that we've been following religiously, and we can use all of the data set to generate these residuals and validate these assumptions. So the first thing I'm going to do is I'm going to generate predictions for all of the data available, which, if you remember, lives in our x variable. So I'm going to call this preds all, and I'm going to use our fitted linear regression model to predict the variables for x. Once we have the predictions, we can calculate the residuals, which, remember, the definition of a residual is the difference between the true value and that generated by our regression line. So we're going to call this variable the residuals, and it's calculated as the true value, which is stored in our variable y, minus those predicted by our linear regression, which live in the variable we just created, preds all. And once we have our predictions, all we need to do is just plot a histogram to verify that they're normally distributed. We can do that with Seaborn's distplot function. That's great. It seems like our residuals are indeed normally distributed. Before we move on, I just want to show you a quick trick. Once again, if you feel like the amount of bins here that Seaborn calculates automatically is too coarse for you and you want some fine grain control, know that the number of bins used in the distplot is customizable. So let's just see an example. If we do a distplot of the residuals, setting the number of bins equals to 50, we can get sort of fine grain view of these bins, and still the answer is still the same. If you see this density estimation is still the same as above, but here we get a little bit more detail. Still, this seems to be normally distributed, so normally we would be happy to consider this assumption as validated and move on. However, I want to take this chance to show you another way of checking whether a distribution resembles a normal distribution, and that's to use a QQ plot. The Q's in QQ plot stand for quantiles, and a quantile, dividing a dataset into quantiles, simply means dividing it into groups that contain the same number of points. So for example, you can take your data and split it into two quantiles, each with 50% of the data. You can take your data and split it into four quantiles, each with 25% of the data, and those are called quartiles. So what the QQ plot is going to do is it's going to take your data, split it into quantiles, take a true normal distribution, like a pure normal distribution, divide it into quantiles, and then compare those quantiles. If the quantiles line up, then that means that our distribution resembles a normal distribution. If they don't line up, then it means that our distribution is not normal. We're going to use this QQplot function that's available in the stats model package, and the syntax is very simple. All you do is you call QQplot, pass in the residuals, and these extra parameters that I'm adding here is just to help us draw a line at 45 degrees, and if all of the dots, all of the points line up along this line, then it means the quantiles match and our distribution is normal. If they don't line up, we have a problem. So this is the result. here at the bottom we have the theoretical quantiles derived from the true normal distribution, and up here on the y-axis we have the sample quantiles derived from our distribution. We can see here that all of the points line up nicely along this 45-degree line, and so we're happy once again to validate the assumption of normally distributed residuals. If you're interested in QQ plots and want to use them in your own project and want to know how to diagnose your QQ plot when the points don't line up in this line, I recommend you go to this article in the completed notebook. The code here is written in R, so don't worry if you don't understand how the code is generated, but it provides some really nice visuals of what happens when we have different types of distributions. So in this case, when the true distribution, as shown by the histogram, matches a true normal distribution, as shown by this red line, all of the points line up along the 45-degree line. That's what we saw in our code, so that's good. It means the distribution is normal. But if we start deviating from a normal distribution, say your distribution is skewed right, you might expect this type of behavior along your QQ plot. If your distribution is skewed left, you expect this type of distribution. If your distribution has fat tails, like this, that sort of overflow those of the normal distribution, then this is the behavior you might expect. If it has thin tails, and so on. So this is a great article with a lot of possible distributions and what we expect to see in the QQ plot. So that's it for the normally distributed residuals. We have two more validations, two more assumptions to validate. Those are homoscedasticity and independence. Let's spend a little bit of time defining them. Homoscedasticity just means equal variance of the residuals across any value of the prediction, and independence means that there is no pattern. There's no autocorrelation in those residuals, so that we cannot use one residual to predict the next. We can actually validate these two assumptions simultaneously using the same plot, and all we need to do is just create a scatter plot of the residuals versus the prediction and make sure that there's equal variance and no noticeable patterns. So we can do that easily using our scatter plot, where we're going to plot the predictions on the x-axis and the residuals on the y-axis. And we see here that there is more or less, if we were to draw the variance lines, they would be pretty parallel, meaning there's equal variance across the range of the residuals. So we have homoscedasticity, and there is no noticeable pattern here in these residuals that would allow us to predict the next value based on one. They look very random, so we validate independence.